So if you recall yesterday, this was the expression we finally got, right? And this is the update rule we're gonna follow in sigmoid neurons. Now, in today's lecture, we'll briefly see how would we calculate the partial derivative of loss with respect to W and partial derivative of loss with respect to B. Okay. So yesterday I told to do some, quick check on the derivative concept. I'm hoping that you have done that. Because if you're not really clear about the derivative part, this part may be a pain for you. Okay. So again, here these are two ways we can deal with this. If you are familiar with derivative concept, then probably you can focus on the mathematical intuition part as well. If not, then you can directly focus on the result also. Okay. Now, first of all, let us see how do we compute the partial derivative of loss with respect to W. Okay. So I'm hoping that you know there's difference between partial derivative and normal derivative. Okay. So first of all, this is my loss, right? This part is my loss. Do you agree with this?
Yeah.
Now what I'm doing is I'm just putting half in front of it. Okay. Putting half in front of me will not impact my answer. So I am putting half in front of it so that it simplifies the mathematical computation. Okay. Now this function, this loss is a function of two parameters, right? It is a parameter of W, it is a parameter of B. Now, when we have to do the partial derivative of loss with respect to W, we have to keep the B term as constant, right? So if we'll do the partial derivative of this with respect to W, right, here there are some standard formula for taking the derivative. For example, if there is a function called x square, if you have to take a derivative of it, what is the derivative? 2 of x, right? Similarly, if you have to take a partial derivative of some function like x minus y whole square, if you have to take partial derivative of this function with respect to x, what will be the partial derivative? This will result x minus y minus y. No, this will be 1. Am I correct? Any math genius can confirm this? This is correct.
Two is missing.
Yeah, sorry. This 2 is missing. Correct?
So that's the derivative of x minus y square?
Yes. Yes.
Okay.
Yes. This is not a derivative of x minus y square. It is a partial derivative of x minus y square with respect to x.
Oh, okay.
Right? Because we are treating y as constant. Okay. So same thing. Same thing I'm applying here also, right? And if we'll do the partial derivative, I want you to do this in your notebook. Then only you'll be able to understand. Okay. So the same thing you'll apply here. Finally you will be able to get resolve this into this expression. Now, what is my fx? My fx is nothing but the expression for sigmoid neuron. This is my fx. This part is my fx. Okay. Purposely, I'm not explaining this thing in a detailed way because tomorrow I'm going to take one separate class on derivative. Either me or Uzma will be clearing the concept of derivative in tomorrow's session. So for today, anyways, I have explained what exactly we are trying to do here. But the detailed steps, if you're really worried about, please try to do this in your notebook. If you are not able to do it, we will be doing one session on derivative tomorrow. Okay. But for now, you can understand that the partial derivative of loss with respect to W, it will be resolved into this equation. Okay. And when you will take the partial derivative of this expression with respect to b, then the answer will be same as this one, only this x part will knock off. Okay, so just take care of these two things. How do we compute the partial derivative, right? If you're not able to do, if you just wanted to remember the result, still it is fine. Just remember that this is a partial derivative of w, sorry, loss with respect to w. For partial derivative loss with respect to b, same expression will be there, only x will not be there. Is it clear?
Yeah.
Okay. Now I think we have completed our perceptron, sigmoid neuron completely. Now whatever thing that we have learned, we will go ahead and apply in Python. Okay.
Can you go to the other sheet before this?
Yep.
Yeah. So in the end you wrote delta b is equal to f of x star, right? Fxi, this one. So why you're writing that?
This one you're seeing?
Yeah.
Yeah. So same thing when you will do for same thing when you do for b, this will be the final expression. You can get.
Okay. No, but you added a summation here on top. There's no summation, right? So I was thinking.
Yeah. So here also you have a summation, but just to simplify, the notations are not including. So this is doing update for one iteration. But if you have to do n iterations, obviously you need to put summation, right?
Yeah, then it will be I to 1 to
Yes.
n fxi, right? Okay.
Yep.
Okay, got it. And then on the right side, what
Yep.
what are we doing here on the right side?
So this expression, this expression is consist of fx. And what is my fx? My fx is nothing but 1 upon 1 plus e raised to minus wx plus b, right? So this is the partial derivative of that expression with respect to w.
Oh,
Right.
so after applying all this, we are coming to that final conclusion.
This is your final conclusion. However, to reach this final conclusion, you need to know the partial derivative of fx, right?
Yeah.
So in the separate part, I am doing that. You can directly plug that result here and finally get this expression.
Okay. So there is nothing new. I mean,
No.
what it is doing is it is just solving and coming to that conclusion that you told.
Yes.
Okay.
Yeah. Nobody is going to ask you this derivations. Normally, people are interested on more implementation side, but still, we'll see how exactly we are getting this thing through detailed approach. Okay. Now let's head over to the implementation part, because this is the major focus of today's class. Right? So here I am taking one example. I'm having a data which is having two records, right? X1 and X2, Y1 and Y2. Okay, so if I have to represent this in tabular form, I can write it like this. I'm having X1, X2, and this is Y, this is 0.5. Wait, it is only consist of one term, so just X 2.5 and here 0.2 and 0.9. If suppose this is my data set, it is consist of only two observation, two record. Okay, then how would we solve for the optimal value of W and B using sigmoid neuron? Okay.
Why is the output target
Yes.
output?
Yes, whenever you see Y, just immediately think that it is an output. In
Okay.
entire machine learning, Y is specifically reserved for output. In most of the cases, you will see Y as output. Okay, unless specified, consider Y as output. Okay, so this data part is clear. How the data would look like. Okay, now let me change the ink here. Okay. Now, if I have to do this using perceptron, sigmoid, I can resolve this entire big problem into multiple chunks, right? And I'm writing one function for doing each part of my chunk. So first of all, I need to compute y hat, right? I need to do y hat. What was my formula of y hat? My y hat was 1 upon 1 plus e raised to minus wx plus b, right? This is y hat. Also, you can say it as a y pred, right? So this is the function for computing my y hat. Okay, this function computes my y hat. It takes three input w, b, and x. W, b, and x, right? And it returns y hat. Okay. Then I have another function for computing the loss. Okay. So what was the formula for loss? The formula for loss was what? It was, y hat minus y whole square. And then we applied half in front of it just to reduce the computation. And this I have to do for all the records. So there was summation. I is equals to 1 to n. This is how my loss is calculated, right?
Yes.
So this function is computing my loss for one iteration. Okay. First of all, this function will call this function, which will give you a y hat. Y you already know, it is present in the data itself. It is just putting into this formula. It is just putting into this formula here and computing the loss of one iteration. Is it clear? Just look for it for a second and let me know if you have any doubt. Okay, no doubt. Then let's look at the third function. So now what this third function is doing, it is computing my partial derivative of loss with respect to b. This is what? dl by db, right? We know this because because it is required for doing the update, right? And we already know what is my dl by db from the previous slide. So just I have put the formula here, the formula that we got for dl by db. The same thing I have done here also. So here what we are doing, we are doing that dl by dw. From the previous slide, we have the value of dl by w. I'm just putting the formula for that. Okay. Now finally, I am having the final function, okay, which is known as a driver function. From here, the actually program will start. Whereas all these functions are the helper functions, the remaining functions. Okay. As per the algorithm, we have to initialize the value of wb and eta something. So I have initialized -2, 1. By the way, eta is also called as learning rate.
And these random assignment is just random, right? You could have even taken -1, -1 also.
Yep. These are just random values. Okay. You have to initialize your process with some value.
It can also be positive value.
It can be positive and it can be negative value. Anything.
Okay.
Just don't take irrational number. Any real number it has to. Irrational number you can also take, but it will unnecessarily make things complicated. Okay. Now I have to do these iterations for 1,000 times. Okay. I want to update my value of w and b for 1,000 times. Doesn't matter whether I reach the convergence or not, but I will do it for 1,000 times. I have initialized that. I have defined that. Okay. So first iteration, coming to the first iteration part, right? What I am doing is initially my d, w, and db is 0. Initially, even before the first iteration, it is 0 because I haven't updated anything, right?
Yeah.
Now I am computing dw and db, right? What is my dw and db? dw is partial derivative of loss with respect to w and partial derivative of loss with respect to b, right? So here I'm computing dB and dW. Once I get the dB and dW, I can update by W, right? W is nothing but what? W is equal to W minus eta dW. This was the formula I had, right?
Yes, from yesterday's lecture.
Right? My this is what? As per the function, this is my dW, which is what? dl by dW. And what is my eta? Eta I have written as eta and I have defined it as 1. So I will update W and B. And since I have defined a for loop that will go from 1 to 1,000, this W will keep on updating till 1,000 times. Yeah. This flow is clear.
Yeah. But in the last function, right, do gradient descent. So when we are for x comma y in zip x comma, sorry, for I in range till max epoch, right? For 1,000 value, we keep on updating the DW, right?
Yes.
So that means after 1,000 times only the final value of DW is getting used in the formula following that, which is W equal to W minus eta into DW, right?
No. See, DW is getting updated 1,000 times. You see, this update is one indented from your this for loop.
Yeah.
Right. So this is something like this. Let me do this a pictorial representation for you. Here, this is iteration 1. Okay. You have got some value of W, 0.1 and B, 0.2. Okay.
Yeah.
By updating W and B. Now this is iteration 2. Okay. Now this will update to some 0.2, 0.4. Now update 3, iteration 3. This will update to some 0.3, 0.7. This way it will keep on updating till 1,000 times. And the final value which will have of W and B will be the value which will have in 1,000th iteration.
Okay, so the outer for loop is where the value of W and B are getting updated for every iteration.
Yes,
right?
yes. See this.
Okay. Yeah. Okay, got it.
Okay. So if this algorithm is clear, so now let us do the visual interpretation of it. How exactly this is helping us to get the optimal value of W and B. Okay. So when I was in first iteration. So in my first iteration, what was my W and B value? -2, right?
Oh yeah, -2.
W and B, -2.
Yeah.
Yeah. So -2 is here and B value -2 is here. So here. So you see, by this axis is W, this axis is B, and this axis is loss. Okay. I need to minimize the loss. Okay. So when during my first iteration, my loss was highest, right? Second iteration, maybe the value was somewhere like here. The loss was reduced a little bit. As my iteration progressed, the loss gradually shifted from higher value to lower value, and finally you'll see that my loss value has reached here, somewhere here. Okay. So what it will do is, as you'll keep updating the value of W and B, your loss will reduce. It will reduce, and it will try to reach to the minimal value. In this case, the minimal value is this one, right?
Yeah.
Now, if you had initialized only for 10 epochs, right? Maybe you might not have reached to the minimum point. You might have reduced the loss, but you might be somewhere like here, right? So normally what people does is people keep the value of max epoch a very high number, typically in the range of 1,000, 10,000. Right? So you understand how we minimize loss with every update in the value of W and P?
Yeah, but as per the graph, then the loss is increasing also, right? It goes to the bottom and then it is rising up.
Yes. It happens. It happens. It happens.
Okay.
See, why it happens, I'll also tell you. This is how the curve of usually loss look like. Okay. What happens is initially you are here and you want to reach here. Okay. When this happens, I'll tell you, you have specified the learning rate, which is eta. Okay, eta is 1 here. So you'll in every update, you'll take some step of jump here. Some step of jump here. Okay. Now what happens is, since your jumping step is big, you might overshoot this point of minima. So instead, so again, you have to come back from this position, right? You have overshoot the minima. So that is a point you are you are seeing here. The we first there are some places where loss has increased also marginally, and then it came back down to minimum point. So that is why it is also suggested that you should keep your learning rate low. Here I have taken the learning rate 1, which is a quite big number. It should be it usually should be 0.1 or 0.01 is the learning rate people used to keep. But if you'll keep too small point learning rate, the convergence will be very slow. The algorithm will take very large amount of time to reach minima. Okay, so it's always a trade-off.
So typically, in real world application, how long this algorithm runs for?
Yeah, so it depends upon the complexity of problem you're having. So, for example, if you're working on a problem which is a very high dimensional data, for example, here we have just taken one value of x, right? But if you are working with a problem where there are large number of x, for example, if you're working on some DNA sequencing and all, genome sequencing, so there you'll have the number of x typically varies from 1 million to 10 million also.
Okay.
Right. So those are highly computational data. In that, for those kind of problem, you might not use your local system for that. You need to work on big clusters, and for those problems, your algorithm runs for 8 hours, 10 hours, even some days also. Right.
Okay.
But there are also certain problems where your algorithm hardly runs for several minutes and you get reasonable result. For example, you are doing an image classification problem. You are trying to identify cat versus dog image, and that image pixel is like 480 cross 480. So you have 480 number of x, 480 number of features. Okay? So to answer your question, it entirely depends upon the volume of data you are dealing. One is the volume. Second is the dimensionality of data you are dealing. Dimensionality means the number of x in my input feature vector. Right. Third, it depends upon the processor you are using. Right.
Yeah.
Okay. Any question in this?
I just can you explain the error function once?
This one?
Yeah, like how it equates to the loss.
Yep. Sure. Okay. So initially, when I have not done any iterations, my error is 0. Okay.
Yeah.
This is how my data set looks like.
When you say error is 0, you mean loss is 0, right?
Yes. Error, loss, one and the same thing. Now, what I'm doing, first of all, I'm traveling my first record, right? I'm computing y hat.
Yeah.
Right? This will compute my y hat.
Which one? Fx equal to
Yeah.
FWBX?
Yes. This will compute my y hat, because this will call this function, and this function is nothing but it is computing y hat, right?
Yeah, y hat.
So y hat is computed now. Now I'm just simply putting the formula here. What is that formula? Y hat minus y whole square. And I'm putting half in front of it for doing, simplification of computation.
Okay.
Is it clear?
Okay, I think, yeah, it is clear. It's clear.
Okay, awesome. Then I think we will conclude sigmoid neuron part. Okay. Yeah, but before we conclude, there's one another evaluation metric for sigmoid neuron. So you have already seen accuracy, right? Accuracy is nothing but the fraction of correct prediction. Okay. But in case of regression problem, where your y, where your target variable is continuous, in that case, you cannot have accuracy. There's another metric which is popularly known as Rmse. Full form of this root means square error. What this matrix says that, or rather I should explain the formula part of it. We have y, we have to subtract y hat with this, square the difference. Okay, wait. This part is familiar with you, right?
That's the loss, right?
Yeah, that is a loss, square error loss.
Yeah.
This part is square error loss, right? Similarly, doing it for all the observation, that's my summation part I am. Then I am taking average. How would I take average? I'll just multiply 1 upon n.
Yeah.
Right. And then I'm taking an under root of it. And this becomes another metric called root mean square error.
Okay.
Lesser the RMSE, better is the model performance.
But why we are doing that? Why are we getting RMSE?
The reason is it is more reliable metric when you are having a continuous output. When your output is a numerical kind of like here you have, in that case we prefer to use RMSE. Okay. Whereas in case of your classification problem, you can rely on accuracy as the metric. Okay.
So here there are two data, right? One is training data, and another is the test data.
Yes. Yep.
So what is test data? Like test data is what we are going to feed into the system?
Yes. See.
But when you're feeding, you are only giving, like in this data, you have like, 4 columns and I don't know, like 10 maybe 10 rows, right? So what do this, how does it match to the training data, right? Training data has like launch, weight, screen. How does it correspond to test data?
Yeah. Here also I have all the features. See, what we normally do is, if you are having 100 record of data, okay, what you will do, you will train your model with 60 record of data. What we do in case of training, we compute appropriate value of B and W. Once we have got the value of B and W, we use the remaining 40 record, which we have not touched, to generate prediction. Okay. Now the question is, why do we split this way?
And how is the split done usually? Like, is it like half?
It's up to you. It's entirely depend upon the problem you are solving. If you are having a huge data, so probably you would prefer to keep 70% for your training, 30% for testing.
Okay.
Sometimes you can do 80-20 split also. But normally it is a general practice that the fraction of data we keep for training is higher than the fraction of data we have for testing.
Okay.
Because we need to feed large amount of data to get the optimal value of W and B. Okay. It is just like we human learning. For example, how do we do learning? We learn through textbook, we solve certain problems. Once we have done the learning, we will sit an exam where the teacher will give you some different questions from the same syllabus, right? So it is just like that only. First of all, we have to teach the model with the help of training data. Once model has learned with that training data, once it has identified the pattern in it, then to check its learning, we feed the test data, the data which was not used in training, but the test data will also have similar attribute. It will be from the same syllabus.
So, Ashutosh, for the test data, right? For
Mhm.
the test data, the second last row, which has 0.17, 0.56, and 3, that is Y, right? That is the like.
Yes,
So
that
for
is,
the test data also, we know the what the like was.
yes, yep,
We had that information beforehand.
yes,
And the last one, the last row is what the Y pred is.
yes, Y hat.
Okay.
Then only we'll be able to compare now performance of model.
Yeah.
If we not
Yeah.
know the ground truth, there's no base for checking whether the model has done correct prediction or not.
Yeah.
Okay. Okay. So now we have two performance metrics. One is accuracy, the other is Rmse. Accuracy is for classification, Rmse is for regression. Okay. All right. So I'll just quickly summarize what are the major takeaway from sigmoid neuron.
So Ashutosh, you didn't tell how it turned out, right? Like I just saw the numbers. Are we not going to make out anything of those numbers, that 0.17 and the predictant was 0.24, then for 0.56 the prediction is 0.67? So is it like good, bad? What do we make of them?
Yeah. So as I mentioned, Rmse, the lower Rmse, the better the model would be, right? So now you have to just put this formula into this equation, and you'll need to compute Rmse. So let me do that. See, this is my y hat, so y, and this is my y hat, right? Now I know the y and y hat. I can put these value into this equation.
Yeah.
Right? And I'll get some value of Rmse,
Yes.
which will be decimal, which will be fraction.
Yes.
Now typically Rmse lies between 0 and 100. I'm talking about the percentage part, right?
Yeah.
Right. The lesser Rmse, the better is the model. So typically
So if RMSE says at 10, means we got a good model.
yes.
Okay.
Right. This just let me do the one correction here. It need not to be between 0 and 100. Definitely it will be more than 0 always, or equal to 0, but the upper cap is not defined. Okay. Let me explain this to you.
Hello, Ashutosh.
Yes. Yep.
Will the RMSE lie between 0 to 1?
No.
If not in percentage, if it is written in decimal, will
Not
it lie
always.
between 0 to 1?
Not always.
Okay.
It depends upon the scale of data you are having. So here you see the scale of data is in decimal. It is in very small scale, right? So your Rmse will be also very small. But instead of this, if we have the data of your salary, then the Rmse, Rmse will be typically in the range of thousands, right? So Rmse. So just try to understand here what is the physical interpretation of Rmse. Rmse tells that how much your prediction is deviated from the true value. It is somewhat similar to standard deviation. Are you able to make sense out of it? If your true, yes.
Hello.
Yep. Tell me.
Yeah. So basically, what I understood from this table is like if the sigmoid function is greater than or equal to 0.5, it outputs 1, right?
Just a second.
Or less than 0.5, it will give you 0, right? Output.
Yeah, that is a wait. You're saying that no, it is up to us. Sigmoid will always give you value between 0 to 1.
Yeah, but output like it gives like for binary output, right? 0 or 1.
If you set a certain threshold, in that case it will be 1 and 0. Right? If you set a threshold, you say that any output which is more than 0.5, I'll consider it as a 1. If it is less than 0.5, I'll consider it as a 0. Then
greater than 0.5 or equal, greater than or equal to 0.5, which one is true?
greater than
Correct.
equal to 0.5.
Greater than or equal to 0.5. Okay.
Right? But here
Yeah.
I'm not setting any threshold here, because here I'm more
yeah.
focused on doing some regression problem. Right?
Right.
Yeah. So that is why we are having here Rmse as the metric. What was your exact doubt? I was not able to follow actually.
Not this one. When I was thinking, like when you said, when you're talking about threshold, that's how we have to understand. I just wanted to ask you.
Okay. Is it clear now?
Yeah.
Okay. Yeah. So your RMSE is the deviation from your true result. Let's say that for any record, your true label was 100, but your RMSE is, let's say, 0.2.5, right? That means your prediction is likely to be on an average 2.5 meter, either